Well, welcome back again. We have introduced likelihood in the framework of other statistical theories of inference. We've done examples and derivations and properties, and we've talked about uncertainty, which is essential every time. And so now you can, at least in a very simple case, estimate, specify a model with all of its component parts, use the likelihood theory of inference to estimate the parameters of the model. So you're specifying essentially a class of models. The maximum likelihood will enable you to pick a member of the class based upon the data. You can then express how uncertain you are with respect to those parameters. Now we have to present our results. So I'm going to show you how to present the results with statistical simulation, which will be a very valuable tool, not only for this, but for evaluating likelihoods and calculating features of probability distributions and lots of other things. But right now we're going to use simulation for likelihood, for presenting likelihood, for interpreting likelihood. Okay, so simulation from likelihoods. Let's get started. So there we go. So parameter simulation for any maximum likelihood model works as following. Any maximum likelihood model. First of all, we're going to assume the model is correct. We are going to come back to this. We're going to deal with that. If the model might not be correct, we'll have to deal with that. We're then going to write down the likelihood given the model and calculate the maximum likelihood estimate. We know how to do that, at least in principle now. We need much more experience to get a feel for it, to understand how to do it, to make sure that we can do it in a new model. We're going to call that maximum likelihood point estimate theta hat. The properties of theta hat as n gets large, I'm putting this all in context, of course, and it's a little bit of a review. The properties of theta hat as n gets large is the distribution of theta hat, the distribution of the sampling distribution of theta hat across repeated draws of the same data set, of a data set from the same data generation process, collapses to a spike over theta. The standardized sampling distribution of theta becomes normal. That's the central limit theorem. The quadratic approximation to the log likelihood from the second derivative gets better and better. The true variance of the sampling distribution of theta hat is V, variance of theta hat, but that's unknown because it's the true distribution of this parameter if it is applied to each of the data sets that are drawn from the same data generation process, but you only see one of these data sets, so you can't calculate V of theta hat. You'd like to know it. So we can estimate it, it turns out. That's V hat of theta hat. So the estimate of V of theta hat is V hat of theta hat. That's the inverse of the negative of the matrix of second derivatives of the log of the likelihood evaluated at theta hat. You can't possibly have all that in your head right at the moment, but if you go back and you look at your notes or you make some notes from the previous talk or in the book, you'll see exactly this. Okay, so with that setup, we're now ready to simulate our vector of parameters. And this is what we're going to do every time. So how are we going to do this? First, we're going to draw our parameters because the parameters themselves are the pieces of the model that we don't know. All the other parts of the model we've basically assumed. We're going to draw the parameters from a multivariate normal distribution, always from a multivariate normal distribution, regardless of what the stochastic component is, because the parameters across samples follow a normal distribution if the central limit theorem applies. So theta tilde, I'm going to put a little tilde on there to imply, to convey, to denote simulation. So the tilde implies it denotes simulation. Theta tilde is drawn from a normal distribution with a mean and a variance. The mean are going to be our point estimates, which come from the maximum likelihood estimates. So theta hat are our maximum likelihood estimates. And then we got the uncertainty of the maximum likelihood estimates, which are estimated as V hat of theta hat. And that's our variance. So now we have the multivariate normal distribution from which we're going to draw our vector of parameters. When we draw our vector of parameters, one draw gives us k numbers. The k numbers is the multivariate draw. We, at the end of our discussion of probability, I introduced the multivariate normal distribution. So you can go back and have a look at that. That's exactly what we have here. This depends upon the central limit theorem. So it depends upon an asymptotic approximation. It might be wrong sometimes. We'll have to begin to get a feel for when it's wrong and when it's right and when we can rely on it and when we might need some more sophisticated techniques to adapt it to the particular types of other sampling distributions that might arise in particular cases. Let's ignore that now. This is a reasonable approximation in lots of cases. Better and other types of approximations will come up in specific models for specific applications in specific substantive areas later on. So don't worry about it for now. So what's the quantity of interest in any maximum likelihood model? Is it theta? Well, sometimes it's theta. Sometimes theta is the thing that we care about. Sometimes beta in a regression are the things we care about. But sometimes it's not. Sometimes it's the ratio of two betas. Sometimes it's the difference. Sometimes it's mu, basically a predicted value. There's lots of other things that it might be that might be of interest. So we want to be able to calculate any quantity of interest, and we're going to use simulation to enable us, to free us to calculate any quantity of interest so that a computer program does not constrain how we present our results to readers. So a quantity of interest is something you're going to choose, and now we're going to simulate from any maximum likelihood model that particular quantity of interest. Obviously, it's going to be the model that you choose, but the same procedures will apply to any model. So we're going to provide the overview first so you get the big picture. Then we're going to apply it in a very specific case of linear models. We're going to forecast the outcome of the presidential election, or at least I'm going to show you how to do that. And that's in the case of a linear model. And then we'll do it for any quantity of interest. Right, so recall the generalized maximum likelihood model that we set up with a stochastic component and a systematic component with no constraint to linearity or normality or anything like that. We're going to start with that, and then we're going to choose a set of values of the x's. So for each x, we're going to choose one value. I'm going to put a little c at the bottom of the x, the vector of x's, to denote choose. So you get to choose the values. Choose the values because if we want to create a predicted value or something like that, you have to decide what values of the x's you're going to stick in. Then we're going to estimate the maximum likelihood estimates of the parameters of the model, right? And if you look at this model, the parameters here are alpha and beta. Everything else is known. X is supposed to be known. Theta is calculated as a function of, as this function. We know G, we know F. So basically the only thing we have to know here, the only unknowns are alpha and beta. So we're going to use maximum likelihood estimation to estimate alpha and beta, and that will give us point estimates, alpha hat and beta hat, which I'm going to put together as gamma hat just to make it simple. And then we're always worried about whether those are good point estimates of an entire distribution, and so we'll use the variance covariance matrix of those point estimates to summarize how good it is and to convey our uncertainty. We're going to simulate the estimation uncertainty. So estimation uncertainty, remember, is separate from fundamental uncertainty. So first we're going to simulate the estimation uncertainty, and that's going to be by assuming the central limit theorem, using the central limit theorem as an approximation. We're going to have a random draw of gamma, which is the betas and the alphas. It's going to have a little tilde on it referring to simulation, and it's drawn from the multivariate normal distribution with mean equal to the maximum likelihood point estimates and the variance equal to the variance covariance matrix that we just talked about how we would estimate. And then we'll calculate our theta hat sub c, because we're going to put a sub c there because x has a sub c, and since x has a sub c, that propagates through, and now we're calculating a very specific theta tilde sub c. This is very general notation, but you can think of it in terms of a regression. This could be theta would be mu, and g would be linear, and x would be x, and beta would be g of xc comma beta would just be x times beta. But this is just more general. It enables any nonlinear model. We're then going to simulate not only the estimation uncertainty, which we did before, 2 steps above, but now we're going to simulate the fundamental uncertainty given the estimation uncertainty, and that's sort of the key. First, we get estimation uncertainty, we stick it in the model, and we draw fundamental uncertainty. Where's the fundamental uncertainty? The fundamental uncertainty is the stochastic component right here. The estimation uncertainty are the 2 parameters that we need to estimate, but even if you know those exactly, there's still stochastic variability. There's still estimation, there's still fundamental variability. So we're going to do simulation to represent that. So the point of simulation, the way that you know you're doing simulation right, is you have to simulate with respect to all of the uncertainties. And estimation uncertainty and fundamental uncertainty are the key 2 pieces. Obviously, we might also pay attention to model uncertainty, but we're not going to do that. Right now, we're going to be assuming the model. We'll deal with that later. So then, once we have simulated fundamental uncertainty, we now have the outcome of the whole model. We have y of c, tilde, so because it's simulated. From that, we're going to calculate our quantity of interest, right? And that could be represented in any way we like. We have lots of simulations of y tilde sub c, which might be our predicted outcome of the election or whatever it is. We could plot a histogram which represents everything we know about it. We could calculate the mean of it. We could calculate the variance or standard deviation of it. We can calculate the area under the curve to the right of 7. Whatever it is we wish to calculate, we can do that straight from the simulations. That's the incredible flexibility of these simulations, of following a simulation approach to understanding quantities of interest and to presenting quantities of interest. Okay, now let's do an example, a real example. Forecasting presidential elections. Okay, so I'm going to forecast the outcome of presidential elections. We're going to go through, I'm going to slightly simplify a model that I actually used to forecast an election some time ago. I'll show you the results of that. Okay, so forecasting presidential elections. We're going to start with the data. First, we have an index. So I is the index for a person. Normally, but in this case, the unit of analysis is the state year. So we have election results by state. Now, in case you're not an American or interested in American politics, here's just a quick review. Here's the American presidency is not decided by whoever wins the most votes. It's a particular system that is the Electoral College, and the way it works is there's a separate election held in each state in the United States. Each state whoever wins each state gets to allocate the number of electoral college delegates that state has, which is equal to the number of senators, which is 2, plus the number of members of the House of Representatives that it has, which is determined by population. So each state has a number of electoral college delegates. Whoever wins a plurality of the votes in each state gets to decide all of the electoral college delegates in that state go to the winner of whoever of the election in each state. So there's a separate election in each state. Then the electoral college delegates get sent up, winner take all in each state, and whoever wins a majority of the winner of the electoral college delegates gets to run the country for 4 years. There's a couple of little exceptions to this. In Maine, they don't go statewide. They do it by congressional district, but roughly speaking, this is the way it works in almost all cases, and so let's just focus on that. Okay, so index I equal 1 to 50 for the states. There's also the District of Columbia, which we're going to ignore. T is the election year, and the election years in my data set here are going to go from 1948 up to 2016. 2016 is the last year of data there is. We could go back before 1948, but if you go too far back, then it's a really different set of data, and probably the parameters of the model are really very different, and so it doesn't really add that much. So we'll go back to 1948. It's an arbitrary choice. We might want to see whether your results are dependent upon that choice. Y of IT, that's going to be the outcome. That's going to be the democratic proportion of the two-party vote in state I and year T. So we really care about that. Whoever gets the majority there, the plurality there, gets the electoral college delegates. At the moment, we're just going to imagine there's only two parties. In reality, there are often more candidates than those two, although there's usually only two major party candidates. Then we're going to have a set of covariates, of predictor variables. We're going to have a constant term, but we'll have economic conditions, unemployment, GDP, polls that are available, the home state advantage. Usually there's a friends and neighbors effect of the presidential candidate is from a particular state. That state would very much like that candidate to be elected a little bit more than they would normally. Same thing for the vice president. The ideological position of the candidate relative to the ideological positions of the states is also very important. You can put other variables in there also. Those are the main ones. Also, of course, the vote the last time. Then we're also going to have one other set of data, which is the 2020 values of x sub I 2020. We don't have y sub I 2020. That's the thing we want to know. But for x sub I 2020, we have the same values of all the covariates, but measured basically now, because we're trying to figure out the outcome of the presidential election. And then we know the number of electoral college delegates in state I in 2020. And I'm going to call that C sub I for electoral college delegates. And that's a known number. That's just a fixed number. As I said, it's the number of senators plus the number of members of the House of Representatives. Okay, so that's the data. We have to figure out how to put that together in a model. I'm going to, as I said, slightly simplify the model that we're talking about. So here's the model. Y of IT is going to be normally distributed with mean mu IT and variance sigma squared. So that's going to be the setup. That's going to be the stochastic component of the model. There's also a systematic component, and the systematic component is going to be linear. So mu IT is equal to x of IT beta, where x of IT includes a constant term. And then we're going to have an independence assumption where y of IT and y of I prime t prime are going to be independent for all I not equal to I prime and t not equal to t prime given x. Okay, so basically we have independence across states and time periods. Okay, so before we build the likelihood model and then figure out our quantity of interest and estimate it and show you all that, it's important that you evaluate a model and don't just take it as given by me. Evaluate it, figure out what the weaknesses of this model are. Okay, so look this over and see what are the weaknesses. What are the things that you don't trust? Now, there's a lot of things that aren't correct about this, that aren't true about this, because after all, it's just a model. The question is, what parts are not so useful? What parts, if you changed, would really make a big difference, and the change is something that you may or may not even be willing to defend one way or the other. Okay, so what are those things? Think about that. Okay, it's worth pausing, like pressing pause. Okay, here's what occurs to me. Okay, so y might not be normal. I mean, normal is just an assumption, right? I mean, who knows? In fact, y isn't normal for sure because y is the democratic proportion of the two-party vote ranging from 0 to 1, and the normal distribution is unbounded. It goes from negative infinity to positive infinity. So for sure that assumption is wrong. However, it tends to work pretty well because the model fits the data in the region in which the data exist, and it tends not to go beyond the bounds of the possible. It doesn't go outside of the 0-1 interval, or at least it doesn't go that far out. So you can change that assumption, and it probably wouldn't make that much of a difference. That's a good example of an assumption that's wrong, but useful. You can look at the list of covariates and think about whether there's other things that belong in there. Should you put pandemic in there? Right? Well, I don't know. And if you do, I don't know exactly how you put it in, right? Because you know what? Every election, we look at the election and we say, this year when we're forecasting it, this is an extraordinary year. Every year, every election year, it seems that way. Well, this year, it seems like an extraordinary year. But we always say that. But really, this is an extraordinary year. But we always say that. Okay, so I don't know. You're going to have to decide that. So the list of covariates matters a lot. What else? Well, we're assuming that the relationship is linear. Is that really right? Are there no interactions? Should there be? It's easy enough to put interactions in there, right? Are there nonlinearities that should be there? Should we put squared terms in there? Does that matter? Or would we be fitting the data too well? So if you fit it too well, then you're fitting idiosyncrasies in the data rather than systematic components that persist into the future. Those are the things that would be useful for forecasting. So if we fit the model to a very flexible functional form, we might what's called overfit, which is fit the idiosyncrasies rather than the systematic pieces. Is that what's going on? We don't really know, right? You'll have to really think about that. Okay. Finally, we have this independence assumption, number 3 here. So, is state I in time t independent of time t minus 1? No way, right? New York is going to be more liberal. Washington, D.C. is going to be more liberal than Georgia is, than Utah is, right? I mean, both of them are going to be, there's going to be time series dependence. It's probably also the case, in fact, we know it is also the case, that if New York and New Jersey are, right now we're assuming independence between New York and New Jersey. So if one of those goes up in a year, would we expect the other one to be independent? No, we'd probably expect that one to go up as well, to become more democratic or more Republican. So these are the places where we're going to be making mistakes. We're going to be simplifying. The actual model I ran was a little bit more sophisticated than this, but not a lot. And so this does capture the main features of the model. Okay. And of course, I want to keep it simple for now so that we really understand what it is we're doing. All right, so here's the likelihood model. We're going to write that down from the statistical model. We're now going to derive the likelihood model. So the likelihood of the parameters mu sub I t and sigma squared, given all the data, is proportional to this normal distribution, which is the stochastic component. That's the actual formula for it, for the I-teeth observation. Then we form the likelihood for all n observations. How do we do that? Well, we use the third assumption of the model, which is independence. And it's independence over n and over I and over t. So that's why we have two product signs here, right? We could put it all in one index and say it goes from I equal 1 all the way up to n times t. Or we could just do it this way. Same sort of thing. Then I'm going to put in the formula. That's the formula. You've seen it before. It's just the normal distribution. Okay. Now let's take the log likelihood. It's the log likelihood of the equation I just showed you. We take the log of the likelihood. So we have to take the log of this whole thing on the right-hand side. It's the log of the product, which is, that's right, the sum of the logs. So now we have the sum of the log of the likelihood. So now I'm going to substitute in the formula for the likelihood and take the log of it. And that's what we get. We just stuck the formula in there. Now we're going to take the log of the two pieces. And that's the log of the two pieces. By the way, one little formula I haven't shown you before is the log of this first, well, let's see. First of all, it's the log of the first piece plus the log of the second piece. That's what we have down here. And the log of the first piece is the log of a thing with an exponent. Okay. So a thing with an exponent, the rule is you take the exponent, you put it out front, and it's the log of the rest. So that's the way it works. And that's exactly what we have there. Then we break apart that thing because we have now the log of a product. And so we have 2 pi here and the log of sigma. Now remember, sigma squared and mu are the 2 parameters that we're going to want to estimate in this thing. Pi is a fixed number. It's not a parameter. So the log of 2 pi is a term. It is red. It turns red because it gets embarrassed, goes away, right? All it does is shift the likelihood up or down, so it does not matter. Notice the red or crimson mu sub I t. Now we're going to use the second assumption in the model, which is the systematic component. And the systematic component is that mu sub I t is equal to x sub I t times beta. And so we've substituted it in. This is another example of reparameterization. So we've reparameterized mu of it into x sub it beta. Now notice here, there's n times capital T of these, but there's only k of these. So in the simplest case that I showed you, we had n mu's, and after we reparameterized, there was only one beta. So we're also reducing the parameterization here from n times t down to just k of these. But it doesn't go down to 1, it just goes down to k. And k, which is the number of explanatory variables or number of variables in the X matrix, is a relatively small number. Okay, so this is the log likelihood. It looks like the simplest log likelihood that we've given you before when sigma squared was just 1, in which case this goes away, and this is just 1, and we basically have the least square solution. So we're still going to have a least square solution. It's going to just be a full least square solution with a sigma squared. Okay, so now we're going to do estimation. To do estimation, not the way you learned, but to do it generally for any statistical model, we're going to reparameterize again. We're going to reparameterize the parameters that are bounded, and sigma square is bounded, which means it can't take on any value. Beta can take on any value, at least in principle, but sigma squared can't. It can't be 0, it can't be negative. We're going to reparameterize to an unbounded scale. Doing that are numerical optimizers. Remember I said we're going to find the optimum, the maximum likelihood estimate, by numerical means. Well, we have to make it a little easy for the computer programs that do this kind of thing because they need a little help. So the numerical optimizers work better if you reparameterize to the unbounded scale. Also, the central limit theorem kicks in faster. That is, you need fewer observations before this approximation works, which is great. As I said, beta is already unbounded, but sigma squared is bounded, so we'll have to deal with that. How do we transform it? So one way, there's other ways, is we take sigma equals e to the eta, and I just made up a new, I just chose a new Greek letter. And the interesting thing here is if we estimate eta, no matter what eta we stick in here, we get a sigma that's greater than 0. So that's a great thing. So now our optimizer, which expects and likes and works better with an unbounded parameter, now has an unbounded parameter. We tell it, please find the maximum likelihood estimates of eta and beta, all of which are unbounded, and it'll just work better. Okay. How do we do this? Well, let's stack up the betas and the etas and put them together, and we have gamma. So we'll just put them all together, makes it easier. That's a k plus 2 times 1 vector. Why is that? Well, it's k for the betas plus it's k, it's the number of explanatory variables plus 1 for the constant term plus 1 for the eta. Okay, so however you want to calculate that. We're going to turn the log likelihood into code. So you have to figure out how to do that. We're going to maximize it. How are we going to maximize it? You're literally going to take that code and you're going to put it into a function, and the function is going to find the maximum for you. What are you going to get? You're going to get point estimates for everything in gamma, for the betas and for eta. And we're going to save those maximum likelihood point estimates. Then we're going to have uncertainty estimates. The uncertainty estimates will be the variance covariance matrix of gamma. And then let's look at the R code. Okay, so how do we do this? Here's the mathematical form, which I've shown you before. I derived this before, so I'm just printing it here again. And we have to put this into code. That's the code. You can pause and have a look at that. It's just creating a function, which I've called log-like because it is the log likelihood. We can call it anything we want. This is one way of writing down the R code so that in goes the parameter values, which is going to be gamma, which will include beta when you pull off this piece, and it will include sigma squared when you pull off eta and exponentiate it, then it turns it back into sigma squared. Okay, so those are the pieces of what the log likelihood does, and then the last line of this computes this expression here. And what gets output is the log of the likelihood. It's the height of the likelihood surface given the parameter values, and also the data x and y. Now the data are fixed in any one problem, but you might as well write it generally so you can stick those in different values when, so you can run it differently for different data sets. But when we give this procedure to the R function that will optimize, called optim, we won't even have an X and Y. We'll just stick the data in there, and you really only tell Optum, pay attention to par, which are the parameter values. Okay. So now, forget about this other function. Let's think, how do we do it by hand? Well, you could call the thing, right? So each of these is a different call to this log likelihood function. So the first one, in each one of these, I'm imagining we have parameter 1, 2, 3, 4, 5, 6, 7 parameters, okay? So now suppose you have 7 parameters. It's your job to find the highest point of the log likelihood surface for all 7 parameters. So you can guess the values of the parameters and try to find the top. One analogy that is always used to describe this is, let's suppose there's only 2 dimensions, that is 2 parameters. So we have theta 1 and theta 2. So we have theta 1 east-west and theta 2 north-south. And we want to find the height of the likelihood surface, and there's a mountain. So you blindfold yourself and you walk around and you try to find the maximum. So how do you do that? Well, you take a step to the left and a step to the right, and left is higher than the right, so you go left. And you keep doing that, okay? And eventually you can get to the top. Now, how do you know you can get to the top? You can get to the top if there's no local maxima. So that is, if it really is normal, no problem, right? Because if you know the left is higher than the left is definitely the right direction to go. But otherwise, it's not necessarily the right direction to go, okay? So in other words, you could be on top of a little anthill with Mount Everest over there, and you could think you found the maximum, but you didn't. So you have to be careful of local maximum. In any event, how would you do this by hand, right? Well, by hand if you had this function. How would you do it? Well, you might set all the parameter values at fixed numbers and take one parameter and just keep adjusting it all the way up and down that one-dimensional thing until you found a maximum, and then fix it and keep all the parameters fixed except for the second one and move that one. So that's one algorithm, and it turns out there's lots of algorithms. There are more sophisticated algorithms. We don't need to worry about it. Numerical optimization, which is exactly what we're describing here, is a whole field of endeavor. You could write an entire dissertation, spend an entire career on numerical optimization. If you want to do that, go for it. Come back and let us know what you found. But in this class, we don't really need to spend a lot of time worried about it until we have a function that doesn't optimize the usual ways, and then we're going to pay a lot of attention to it. So it's going to be a resource when we need it. Okay. In general, of course, we're not even going to do this by hand. We're going to take this function, we're going to give it to this other function, Optum, and Optum is going to do this for us. Okay. So what are the quantities of interest in this election data set in order to figure out how the outcome of the election comes out? Well, what are the quantities of interest? What is it that we want to know? There's no right answer, okay? Here's the way that I think about it. Here's the reasons we care about the regression coefficients, the betas from this regression, okay? And the answer is everybody thinks we should care about it because it's the thing we're running, it's the thing that the computer program would give us by default. And what are the reasons? And the answer is N-O-N-E. None. There's no reason that you should be interested in the regression coefficients. The regression coefficients don't tell you the things that we actually care about for this analysis. What we care about is who's going to win the presidential election, not the coefficient on GDP. Right. So the predictive distribution of Democratic Electoral College delegates is an interesting and potentially useful quantity of interest. We might want to know that. The expected number of Democratic and Republican Electoral College delegates, we would want to know that. The one that I think I would focus on is the probability that the Democratic candidate or the Republican candidate, it's one minus the other, is elected. It's the probability that the Democratic candidate gets more than half of the Electoral College delegates. We're going to predict the allocations of Electoral College delegates. How are we going to do that? That's really the question. The core piece of that question is how to simulate predictions of the number of Electoral College Democrats the Democrats and Republicans will win in each individual state. How are we going to do that? The options are that are the following, and some of them are actually completely wrong, but lots of people do them, so I want you to really understand it. First one is to use predicted values. Of course, predicted values. We're making a prediction. Why wouldn't we use predicted values? Because it's utterly wrong. Let me explain why. Okay, so so here's the idea. We make a prediction of who's going to win in each state, and if that prediction is greater than 50% of the votes, they win the seat. Now that makes sense, right? If the Democrats win more of the votes, they're going to win all of the Electoral College seats, Electoral College delegates, and otherwise the Republicans get them all. But think about this question. What's your prediction if the predicted values in every state, according to your model, come out at 51% for the Democrats? Are you really predicting that there'll be a landslide, unanimous Electoral College win for the Democrats with a slight sliver of a victory prediction in every single state? Right? That's ridiculous, right? In all likelihood, the Democrats would win 51% of the states, and maybe just a bare Electoral College victory, even if you're right. So what's wrong with the way we have this thing set up? What's wrong is we've ignored the fundamental uncertainty. We've ignored probably also the estimation uncertainty. We have to really understand and include all the uncertainty in our model. Another way is we sort of do it by hand, and we allocate C, the number of Electoral College delegates in state I, times the prediction, the predicted value to the Democrats, and C times 1 minus predicted for the Republicans. This, but what happens if the predicted value itself is uncertain, right? Well, then you're ignoring estimation uncertainty. So the first method ignores fundamental and estimation uncertainty. The second one ignores estimation uncertainty, even though it takes into account the first problem. The first problem I've seen so much in reality. You see politicians make these predictions all the time. What they do, they're not using these formal methods, but they know an incredible amount about their individual districts. And what they'll do is they'll call a district. They'll look at this district and they'll say, yeah, we have more resources than the other party. I call it for us, and I call this one for them. And what they're doing is they're making these deterministic predictions in each case. And individually, they're probably right. But when they add them up, they're wrong. And I can give you, ask me in person, because I'll give you specific examples from specific court cases or specific redistrictings or specific elections in which this kind of mistake has happened quite a lot. It's actually remarkable. Okay. So how might we include both fundamental uncertainty and estimation uncertainty to do this right? Because when you do simulation, when you use simulation to present your results, to make calculations, the fundamental rule is that you always use all sources of estimation uncertainty and fundamental uncertainty. Okay, so what we need here is, to begin with, is the predictive distribution of Electoral College delegates, including both sources of uncertainty. All right, so how are we going to do this? So we're going to simulate 1,000 national elections. We can make it 10,000 too. It's not a big deal. We just change the loop that I'm going to show you. And that's going to produce the number of Electoral College delegates for the Democrats. And then, once we have that, we will calculate whatever quantities of interest we want, average, standard deviation, histograms. So let's look at this algorithm. So for state I, and we're going to repeat this for all 50 states and the District of Columbia, we're going to draw our predicted, instead of a predicted value, we're going to draw y sub I for 2020 from its distribution, from its predictive distribution for state I. And if you look at this formula, this is the predictive distribution of y of I for 2020. And there's a tilde on top because we're going to be simulating from that predictive distribution. It's P of that thing given what? Given all the previous data, right? That's y of IT for previous data, and the previous outcome data, and as well as the explanatory variables for all the previous years and for this year, but not y of I for 2020, because that's the thing we're trying to predict. And this is the probability of the unknown given the data, which is the predictive distribution. Okay, I'm going to show you how to do that on the next slide. But now, for the moment, I'm going to assume that you know how to do it, that we know how to do it, and we're going to figure out what to do with it. And then once we have a feel for what to do with it, we'll go and calculate it. Okay, so what will we do with it? Well, we will take the simulations, not the deterministic predicted value, but we'll take the simulations, of which there will be a lot. And if the simulation of the election outcome, the Democratic proportion of the two-party vote in 2020 in state I is greater than 50%, then the Democrat wins all of the Electoral College delegates in that available to that state. Otherwise, the Republican wins all of the Electoral College delegates in that state. And then we just calculate the total number of Democratic delegates nationally by adding the simulated winnings for each of these 1,000 elections, like one at a time, from all the states. And you just sum them up, and that one there, right, is just, if this thing is true, then this becomes a 1. And then you sum up all the C's for the Democrats, and now we have the distribution, the predictive distribution of Electoral College delegates, from which we can calculate quantities of interest, anything we want. For starters, let's just visualize it. We have 1,000 predictions of the number of Electoral College delegates. We can plot a histogram of those, right? We can look at that. We can see, is the mean of that sort of to the right of 0.5, or the right of more than half the Electoral College delegates, or to the left? Is it a really narrow distribution, all to the right of one side winning, or is it a really wide distribution, so we're very uncertain? All the information's in there. Now we have to figure out how to actually calculate this for each state, and then we have to figure out how to present it all. All right, so how do you draw simulations of Y of I for 2020, including fundamental and estimation uncertainty? So here's how we're going to do it. We're going to choose values of the explanatory variables. So those are our choice, right? That's x sub c, and the x sub c is going to be x sub I for 2020, right? And those values are going to be known. The reason it's actually an effort to make a prediction for an election is you have to scramble to go get these data. They don't just come in a data set. It's hard because the earlier you find them, the more useful your predictions are. So it's a big effort to make a forecast for an election. And as a side point, the best way of forecasting an election is you just wait a little while, then you'll know the answer. So it's not necessarily an incredibly important thing, although if you're involved in the process and if you care about politics, then you probably do want to pay attention to it. I mean, for me, I think of Tuesday night elections as way better than Monday night football, and so it's a really interesting thing. It's a lot of fun. Anyway, choose the values of your explanatory variables. Then we're going to simulate estimation uncertainty. Remember, we have to get to fundamental uncertainty, but first we're going to simulate estimation uncertainty. Where are we going to get that? Estimation uncertainty is the uncertainty in estimating the two unknown parameters, the betas and the gammas, from its sampling distribution. So, so we have right here. This is eta, which is all the parameters from its distribution. Then we're going to pull out beta tilde, and we're going to save it. We're going to pull out gamma, which is our variance, basically, and we're going to unreparameterize it by doing this little thing. So e to the gamma gives us back the sigma, and we save it. And then we compute the simulated systematic component by taking the simulated parameter beta, sticking it in here, and now we have a simulated mu. In the general formula, this is a simulated theta. Okay, so but for now, it's a simulated mu because it's a mean. Then we go from the estimation uncertainty to the fundamental uncertainty. So we use the stochastic component to simulate the fundamental uncertainty, and you take so basically the whole thing here is we're getting estimation uncertainty over here. We're taking that, putting it in the systematic component, and getting out this deterministically, because that's a deterministic calculation. But this is simulated, so it reflects the estimation uncertainty in the beta that gets propagated into the mu. And then the mu goes into here, and then out comes the y, which is the output of the model. So now we've reflected the entire model. The simulation process reflects the entire model. If you can understand how to simulate from a model, you probably understand the model. So it's actually a great thing to do, even just to understand the model. Sometimes you don't quite understand the model, and a good question is, how would you simulate from this model? Because once you understand that algorithm, then you probably understand the model itself. And if you understand the model itself, you'll be able to do the simulation and calculate quantities of interest. So we can now simulate the number of electoral college delegates in repeated elections using all of the appropriate uncertainty, fundamental and estimation uncertainty represented. There's a page here I'm going to leave. I'm not going to describe. And I'm just going to explain to you that there is a way to do what I just described all within a least squares regression program. And you can do that by hitting pause and focusing on this, and that's totally fine. The reason I'm not going to pay attention to it is because I wanted to show you a general way of doing this that will work in linear regression, and in logit, and in probit, and in all kinds of other things. It's true for any one of these models, there may be a faster way of doing it, an easier way of doing it, but what I want is a general purpose method that pretty much always works, because that's much easier, right, across the vast array of statistical models. So this is the way that you would do it for linear regression if you wanted to do it fast. That's fine. This may be more intuitive for you if you're very, very familiar with linear regression. If not, I'm perfectly happy for you to skip this entire page. Okay, so I did this the first time in 1992. I realized that was some time ago, but I forecast Bill Clinton's victory. This is the actual printout from my computer program. Yeah, you'd be happy to know that we no longer use Gauss in this class, so we use R. This is a printout from Gauss. This is the probability that Bill Clinton was going to be elected. We predicted the probability is 0.85. This is the distribution of Democratic Electoral College vote proportions, and 85% of the time, he according to our calculations, he was going to win. The actual error in the Democratic two-party electoral vote proportion was 0.01. That's ridiculously small. The error in the Democratic two-party popular vote proportion was 0.03. Okay, hold on. How big do you expect these errors would be if we could run that election again and look at the results? They would be a lot bigger, okay? Even if we were right on average, and I think we probably were, the error here, the uncertainty in these models is way bigger than that. You know, if you predict an actual election, the Democratic proportion of the two-party vote in congressional elections or presidential elections within districts, or in this case within states, plus or minus about 6% of the vote, is what you would always see. The idea that we're getting this to 1% that's called luck, like a lot of luck. So I thought, let me never make another presidential forecast again. Okay, so you know, it's actually not hard to do these things, and you can always get pretty close. You might not actually forecast the outcome right, because after all, people get to vote anyway they want to vote. And sometimes, as in recent years, the electorate is very closely divided. And even though our predictions show that one party might win or the other party might win, the uncertainty overlaps both. And so I would be willing to bet in most elections, in most recent elections when it was very competitive, that one party was not going to win 75% of the votes. I mean, I would have bet my house that in 2016, neither the Democrats or Republicans would have won 75% of the votes. So we really knew a lot about what the electorate's preferences were, but we didn't really know who was going to win the election in 2016, who was going to actually get to govern. But we knew a lot about the people. So as a democratic politics predictive sense, we knew a lot, but we didn't actually know the thing that we actually cared about. So sometimes you do, and sometimes you don't. We'll see what happens this year if somebody wants to actually put the effort in. Okay, so I'm going to do one more topic, which is extend this linear model to a variance function, which is a model you've not seen before. What I've just shown you was how to forecast an election, but in particular, I've shown you how to calculate a quantity of interest from a regression model where you were familiar with the regression model, roughly speaking, but you probably weren't so familiar with how to simulate from the model. So that was useful for conveying simulation. It wasn't so useful for conveying a new model because it wasn't a new model. Now let me give you a wrinkle on the regression model that is a new feature of a model that perhaps you haven't seen before. So here's a Gaussian that is normal. It was invented by a guy named Gauss. If any of you are from Germany, actually Sasha's from Germany, perhaps you can find some old currency that has Gauss on the bill, and the normal distribution and the whole thing. Anyway, a Gaussian variance function model. Here's the model. Y is normal. Just like in a regression model, there's a mean and a variance. There's a systematic component, just like a regression model. Y is equal to x beta. And a new feature. Instead of a homoscedastic model, homoscedastic means constant variance, sigma squared is not going to be constant. Instead, sigma squared is going to vary over the observations. So how should it vary over the observations? Well, it's going to vary as a function of some variables that you choose. And I'm going to call those z's instead of x's. In this model, the z's could include some of the same variables that the x's have, even all the variables, or it could be completely separate. Sigma squared is a number that is never going to be negative, and so we need some kind of functional form here that respects that. So exponentiating it does that. So no matter what the value of the variables z that you put in here, and no matter what the values of the variables gamma that you estimate, after you put them into e to the to the z gamma, you'll always get out a sigma that is positive. Okay, and a fourth part of this model is the usual independence assumption. The usual doesn't mean that we will always have independence. Sometimes the dependence is the most interesting feature of the model. We'll get to time series models where that's important. Perhaps even we'll have time for spatially dependent models. But here, we're going to assume independence between observation I and every other observation. Okay, so now we have the model. Now let's write down the log likelihood derivation. It's pretty straightforward. We have the same likelihood we had before, only sigma squared now needs reparameterization also. So think about this, right? We have two functional forms. We have two systematic components, one for the mean, one for the variance. We need two reparameterizations then. Both need to be substituted in. And so that's what I did here. For this mu, it becomes x beta. And for this sigma squared, it becomes e to the z gamma. This sigma squared, which is the log of e of z gamma, the e and the log cancel out and we just get z gamma. That is the log likelihood. It's relatively simple in the sense that it's not far from what your experience is. And so we've thought about this one before. Earlier in the lecture, I thought I conveyed in a qualitative sense the idea that there was a variance function, and there could be a variance function. There could be variance function models, and we might wish to predict not only the mean. We might wish to explain not only the mean. We might wish to see what variables have a causal effect not only on the mean, but also perhaps on the variance. Right? In this context, in the context of the presidential election forecast model, it might very well be that that when GDP is higher and unemployment is lower, the mean goes more for the incumbent. But maybe some of these variables also cause a state to produce more variable results or less variable results. And that could be the subject of all kinds of interesting research. Research which I hope you go after and develop your own models for. And that's basically what we're going to be doing next. So we started here with the linear regression models. We generalized it more and more in different ways. We've now seen a model that I think you haven't seen before. Now we're going to go to all kinds of nonlinear models, to logit models and probit models and count models and all kinds of different things. And the great thing is, everything that I've shown you so far, we're going to keep using, right? We're going to simulate in the same way. We're going to assume the central limit theorem in the same way. All of these things, we're going to revisit them. And if it was a blaze of information that you've just seen, and you can't possibly know it all deeply yet, we're going to play it back, because we're going to use it all again to learn the logit model, and we're going to use it all again to learn an account model, and to do each one of these. So as we learn each additional model, we will get these fundamentals in a deeper and deeper sense until it basically becomes really natural. Okay, so I will see you next time. Thanks very much.